Great. Today we are going to discuss marginal distributions. Usually, when you talk of joint distributions, what follows are the marginal and then also the conditional. And when you are discussing joint distributions, there was an example which illustrated that once you have the chain, you can always obtain the marginals. That means for the individual random variables. This was an example on page 114. And we adapted some notations. Of course, we know for the chained, if you have two random variables x and y, this is how we denoted our chain distribution, which is actually bivariate probability. Whereas for the individual, we have the marginal probability, or basically the marginal probability distributions. So when you are using f for the chained, and then we are using f subscript x for the marginal of x, and f subscript y for the marginal of y. Of course, the marginal of x is a function of x, and the marginal of y is a function of y. Then, of course, the joined is a function of x and y. So today, that is what we are going to discuss. Basically, that was an example which we used. So on page 122 is where we are discussing the marginal distributions. So suppose that x and y are random variables with the chain PDF. So this is what you're using for the chain PDF. So we have the event that x lies in the interval AB, where A is less than B. So this event is equivalent to this event because we have two random variables and we are studying them simultaneously or jointly. This event that x lies in the interval AB is equivalent to this event that x lies in the interval AB and just y lies in R, because y is not constrained. It is x which is constrained to lie in the interval AB, but y is not constrained. So these two events are equivalent, you know, and we know equivalent events uh, have equal probability. So if x and y are continuous, and we have said these two events are equivalent, then the probability of the first event is equal to the probability of the latter event because they are equivalent. So they have equal probability. That's why you see I'm saying the probability of the first event is equal to the probability of the second event. And you can see in the first event, it is in terms of the random variable x. So this kind of is actually a marginal probability. But on the right-hand side, it is in terms of the two random variables. So it is a chain probability, where x is constrained to lie in the interval AB and y is not constrained. It is just in R. So to express the chain probability, we have to use a chain BDF. So we have a double integral where y lies between minus infinity to infinity. You can see we're integrating with respect to y, and then x lies in the interval AB. So it is we get that probability using a joint PDF. Now, you can see the first integral. This is the integral of x of y with respect to y. The moment you integrate and put the limits for y, you will end up with a function of x. You will end up with a function of x, which we are denoting as fx of x. So it's actually associated with the random variable x, and it's a function of x. So we shall call this first integral, this function here, fx of x. You can see it's actually a function, will be a function of x alone. And if you look at this function is non-negative. It is actually non-negative, And if you integrate over R, that function fx of x, you'll get this double integral of the joint over R2. That means x lies in R and y lies in R, so we are in R2. And because f of xy is a PDF, this will integrate the 1. So this will be 1. Meaning if we integrate fx of x, we are getting 1. So it means also this is actually a probability density function for the continuous random variable x. It is called the marginal density of x, of the random variable x. So basically, we are actually saying to get the marginal density of x, you integrate the joint over the other variable. Basically, you integrate the joint over y, you get the marginal of x. If x and y are discrete random variables, and we want to define that probability of the first event, that x lies in the interval AB, then x will lie over AB. You'll sum over x where x lie over AB, and then y just over R. So y is not constrained. You can see y is not constrained here in this summation, but x is constrained to lie in the interval AB. Again, you can see if you sum the joint over y, you will end up with a function of x, which we are calling it fx of x. So basically, this is what fx of x, you can see, is also is a function of x alone. So similarly, it is non-negative, and if you sum this fx of x over x, you'll be summing actually the chain over x and y, which is 1, because it's a probability distribution. Meaning the function fx of x is a probability also because it sums to 1 over x over all possible values of x. So this is called the marginal probability function of the random variable x. So in the first case, we considered for continuous, and then the next case we have considered for the discrete. The corresponding marginal of y are obtained by integrating or summing over x for the continuous case and for the discrete case respectively. So these are the marginals. So for the continuous case, integrate the chain over x, you get the marginal of y in the continuous case. And for the discrete case, sum the chain over x, you get the marginal of y. We have examples here. So we have here a chain distribution of two random variables x and y. We have to get the marginal of x. Here saying sum the chain over y. So if you sum the chain over y, this is the result. So you have this actually now the marginal probability distribution of y. You can see we are summing over y. You'll be substituting y equals to 1. Then you have x plus 1, x plus 2, x plus 3, x plus 4. As you vary your index for y, index you vary y from 1 to 4. So you can see you'll be getting 4x plus 10. And then of course, x is takes 1 to 3. So if you were to sum this function over x, you'll get 1. And the marginal proportion of y, you sum over x. So when you sum over x, you'll be having y plus 1 plus y plus 2 plus y plus 3. So you get 3y plus 6. And then y, the support of y is 1, 2, 3, 4. So you have the marginal. So we have the join for x and y. This is the marginal of x. This is the marginal of y. We can also represent the same using a table or in tabular form. So if we have x here, you have these are the possible values of x. You have y here, these are the possible values of y. Whatever you have inside the tables are the join probabilities. You remember? So if you sum along the rows or over y, if you are summing over y, you can see you'll have this column, which is the marginal of x. And if you sum along the over x, you'll be having in the last row, the marginal of y. So actually these probabilities are actually generated by this distribution. These probabilities will be generated by this distribution, whereas these probabilities here are actually generated by this distribution. But you can see the same can actually be found by simply adding over y, or along the row you get for the marginal of x, and summing over the over x, or along the column you'll get the marginal of y. Is so that's first example for the discrete. For the continuous, you have the joint where f of x y is 2. This is the support, and I have the support actually in the remark here. That means in the first quadrant, the shaded region is the support of that joint BDF. The shaded region is the support of that joint BDF. So if you integrate that joint BDF over this support, you will get 1. You will get 1. So if we are to get the marginal of x, you integrate the chain over y. You integrate the chain over y. And you can see the limits of y is from x to 1. You can see from x to 1. So when you integrate and you put the limits, you get the marginal of x. And the marginal of y, you integrate the chain over x. And the limits of x, you can see the limits of x here is between 0 and y. Those are the limits of x. And actually, you can actually depict them also on this diagram. So if you integrate, you get 2x, you put the limits, you get 2y. So you can see, whereas the joint BDF is 2 over the shaded region, the marginal of x is given by 2 into 1 minus x over the interval 0, 1, and the marginal of y is 2y over the interval 0, 1. If you verify, you can verify they are actually BDFs. If you integrate over the support, you'll find that they are actually BDFs. All right, so this is end of notes 3. I just need to load notes 4 and we proceed. Yes. So I believe visible notes 4, the one I've just loaded.
Yes.
Great. So as I indicated just a few minutes ago, that when you are discussing chain distributions, that is when studying now that there are no variables simultaneously. And when you talk of chain, we are using pivariate to illustrate all this. As I indicated sometime back, that they're going to be extended to 3 to 4 and whatever number. And when you want for the individuals, there are no variables. We are actually dealing with marginals. Now let's see when it comes to conditional distributions. So conditional distributions, so far we have defined the chain distribution of two random variables and obtained their marginal distributions. We shall now consider conditional distributions. Suppose that x and y are discrete random variables having chain probability distribution function f of xy, that is our usual notation. After the value y, lowercase y, of the random variable y, you can see y is capital here, but the value it assumes is lowercase, has been observed. After the value y of the random variable y has been observed. So the random variable y has assumed the value small y. The probability that the random variable x will take any particular value x is given by this. So you can actually see it is actually a conditional probability. You see on the left-hand side, we are saying the probability that the random variable x takes takes the value small x, given that, so it is conditional, given that random variable y has assumed the lowercase y. This is a conditional probability. And basically, we shall actually be calling it uh, conditional probability distribution. So you can actually say, how do we determine that probability? You can actually see this is joined over the marginal of y. So when you are saying we are looking at probability that x given that. So when we are conditioning the one which has already taken place, the event which has taken place, the random variable y has already taken or are assumed the lowercase y. Then you can see in the denominator, we are having actually the probability of y equals to y. Basically, the denominator is the marginal, and the numerator is a chain. So it is a chain over the marginal. So in the numerator, we have the chain. In the denominator, we have the marginal. The marginal will be of that one which has already been observed, the event which has occurred. So using our notation, you can remember the chain. We are using that the chain, the distribution is actually the f of xy, and you can see that the denominator is actually the marginal of y. So we have adapted our notation now for the chain and the marginal of y. Now we want to give it a notation for this conditional probability, so that we also we shall be calling it conditional probability function. So the way we are writing here probability that x equals to x given that y equals to y, so we shall be calling this function, the argument of this function will be x given y. So it will be a function of x for given y. That means y has been observed by the random variable y. So to distinguish the functions, you know, remember we are using the function f for the joint. We are using the function f subscript y for the marginal of y. We are using the function f subscript x for the marginal of x. We are going to adapt this notation. We say f subscript x given y. So that because these functions are different, we cannot write here as f. But it will not be it will not be like this f here, which is used to denote the joint. So these are very different. These functions are very different. In fact, the four of them, the join, the two marginals, and the conditional. In fact, we can also have two conditional depending on which one is which event has occurred. So we shall be saying f. The notation will just be x given y to denote that it is the y which has the event that y has taken some value, and we are interested in determining the distribution of the random variable x. So we shall be saying f subscript x given y, and the argument is x given y. You can see now this lowercase, both of them lowercase, will be basically what we have here now, the showing over the marginal. And remember, when we say that the marginal is a BDF, meaning it is non-negative, so it usually says it's zero otherwise, you know. So when we say it is zero otherwise, this function will be defined to be zero when your marginal is equal to zero, because that is now the otherwise. It is outside the support. It is outside the support of the marginal. So so when the BDF for positive BDF, this is now well defined because the denominator is actually is positive. So this is well defined. So that it will be taken to be zero when in the otherwise, when we are outside the support of the marginal. So this is called the conditional probability function of the random variable x, given that the random variable y has assumed or taken the value small y. So for any possible value, small y of the random variable y, if we sum this function over x, but you can see the numerator is a function of x and y, but the denominator is not a function of x, it's a function of y. So this summation will only affect the numerator. So we shall be summing the numerator, which is the joint, over x. But we have seen that when you sum the joint over x, you get the marginal of y. So you can see that we shall be having the marginal of y over the marginal of y, which you get 1. Meaning when you sum this function over x, you get 1. That means this function which we have defined is also a probability distribution, which we now call a conditional probability distribution of the random variable x given y. Uh, Similarly, if x is any given value, because it doesn't matter which one you want to fix. Maybe you want to fix x, maybe it is the x which has assumed some value, then you'll be talking about the conditional of y given x. So similarly, if x is any given value of the random variable x, say that this is the marginal, then the conditional probability distribution of y given x is, so we shall be denoting by f subscript y given x, and then the argument here is y given x. So this will be the join over the marginal of x, which is defined for positive BDF of the marginal and 0 otherwise. That means outside the support of the marginal. Mm. Oh, we are going to use the just example which we have used a few minutes ago when we found, remember in notes 3, we used this example to determine the marginals. So x and y have the joint probability to do this. What we have found the marginals. We found this marginal of x. Also, we found the marginal of x. So if we want to get the conditional of y given x, we shall divide the joint over the marginal. And this is the result. So this will be now, will be a function of y for given x. So it will be a function of y, it is taking 1, 2, 3, 4 for given x when x takes 1, 2, 3. And also the same can be represented in a tabular form. So you are actually looking at the conditional distribution of y given x, conditional distribution of y given x. You see, y takes 1, 2, 3, 4. Y takes 1, 2, 3, 4. X takes 1, 2, 3. So when you are looking at distribution of y given x, for instance, so if we can write these probabilities in tabular form, like if you substitute y equals to 1, x equals to 1, you get this probability. Similarly, x equals to 1, y equals to 2, you get it like that, like that. So you are saying the first row, you are getting the probabilities when the random variable x has assumed the value 1. So you'll be putting here y equals to 1, you put x equals to 1, you get this, y equals 2, x equals to 1, you get this, y equals 3, x equals to 1, you get this, y equals to 4, x equals to 1, you get this. And you can see if you sum those probabilities, you get 1. Meaning exactly a probability, that conditional probability distribution is actually is a probability distribution, basically. Similarly, for y given 2, you'll get this row, you sum them, you get 1. For y given 3, you get this row, you sum them, you get 1. That's why we are calling it conditional distribution, or basically it is actually probability. So you have actually 3 probability distributions here. We have actually 3 for each given value, we get a probability distribution. So we have 3 probability distributions here, conditional. So the first row gives the conditional probabilities of y given that x equals to 1. The second row gives the conditional probabilities of y given that x equals 2. And the third row gives the conditional probabilities of y given that x equals 3. We know that each of the rows sums to 1, since f of y given x is a probability distribution function over all possible values of y. That's why I say if you sum this function over possible values of y, you can see it equals to 1. So for discrete, it's very straightforward, actually, very straightforward. Let us see what we need to do for continuous, because there's an issue with the continuous, in the sense that we say it for a continuous random variable, the probability that it takes a particular value is 0. So it will render it will render the definition we have undefined, because we shall be dividing by 0, or it will actually be infinity, which is not a probability. So let us see continuous random variable. So if y is a continuous random variable, we know we have said this many times, that a continuous probability, the probability that a continuous random taking a particular value is 0. So if we were to evaluate this probability, that x is less or equals to x, the random variable x is less or equals to x, given that y is equals to y is always undefined. It will not be a probability, because we shall be the denominator, which is probability y equals to y, it will be 0. So it will always be undefined, because we are not getting up, as far as probability is concerned, it will not give us a probability. We shall be dividing by 0, something infinite. It's always undefined. So, but in reality, you can always observe a value. Even if y is continuous, you can actually observe a value. Since one can observe a single value, it is such that y equals to y, it is certainly desirable to have a model with conditional probabilities of events, given that the random variable y is equals to small y, or the random variable y as assumed the lowercase y. Now, suppose that x and y are continuous random variables, having a chain probability density function f of xy. So we shall define the conditional probability that x lies in the interval AB, given that y equals to y. Of course, in this interval, obviously A is less than B. So we shall define this conditional probability. Look at that probability very closely. Probability that x lies in the interval AB, given that, so it is conditional, the random variable y is equals to small y. So there's been observed that the random variable y has assumed the value lowercase y. So we shall define that conditional probability by means of the following limit. This is the case when x and y are continuous. So we shall be saying the limit as h tends to 0. So x will lie in the interval AB, and then we say y lies in the interval y plus h and y minus h. So that when we find the limit as h tends to 0, because y lies in the interval y minus h and y plus h, as h tends to 0, the random variable y is converging to y. So that we now define that conditional probability using this limit. Because as h tends to 0, y is sandwiched between y minus h and y plus h. And as h tends to 0, the random variable is converging to lowercase y. So that we have things which are logical mathematically. Now, remember, how do you compute conditional probability? It's actually the joint over the marginal. So basically, we are saying the joint will be x lie in the interval AB and y lie in the interval y minus h and y plus h. That is now the joint. And then the denominator will be the marginal probability. That means probability that y lies in the interval y minus h and y plus h. Now in the limit as h tends to 0. So we now have, so we just need to evaluate the numerator and the denominator. Remember, if you look at the numerator, is a joint probability. So we are going to use a joint BDF. Whereas the denominator is a marginal probability, then we are going to use a marginal BDF, which is basically the marginal BDF of y. Whereas for the numerator, we are going to use the joint BDF of x and y. So this is exactly what you are doing. Remember the bivariate. So we are saying x lies in AB. That is exactly that. You can see the integral a to b, and you can see here it is dx. This is the joint BDF. So X lies in the interval AB, this is the joint BDF, and you can see Y lies in the interval Y minus H, the lower limit, and the upper limit is Y plus H. Now, because the limits are in terms of Y, we cannot write the joint in terms of Y. Use another variable different from Y. You can now see I'm saying f of x u, where Y was sitting, it is now u. Just for it to make sense, we cannot say f of x of y where and the limits are in terms of y. So we say f of x u dx du. So we are saying we integrate over x, the limits of x are a to b, and then integrate with respect to u, the limits are from y minus h to y plus h. So we shall get that joint probability, which for the marginal, we use the marginal of y because we are this just we need the marginal of y. So we are going to, that's why you are saying here fy. And because the limits are in terms of y, we cannot write here y. We have to change to another variable different from y. So I'm using u. So this u will lie between y minus h to y plus h. So you can see whatever you have here is, this is the marginal probability density function of y. Now, we are going to invoke some theorem, what we call mean value theorem for integrals. We had invoked that some time back. And actually, I've given that also in a remark here, what we mean by mean value theorem for integrals. I've distinguished between the two. In the remark, I've given MVT for derivatives. This is the mean value theorem for derivatives. And I've given here mean value theorem for integrals. You can see for derivatives, he said if you have f, this is just now calculus. If you have f, which is continuous function on the closed interval and differentiable on the open interval, then there exists a point C within the open interval, such f of b minus f of a over b minus a is the derivative of f evaluated at C. That is the mean value theorem for derivatives. If you go for mean value theorem for integrals, if f is continuous function of the closed interval, then there exists a point in the open interval AB such that the definite integral over the function over the interval AB, and then you divide it by the length of the interval b minus a, it is actually f of c. This is what we call mean value theorems for integrals. Now I've indicated here, actually the mean value theorem for integrals can actually be proved using the mean value theorem for derivatives, which I have them here in the remark. It can be proved by applying mean value theorem for derivatives to this function. When you apply mean value theorem for derivatives to this function, you can actually prove this, which I have provided a proof here in the remark. You can have a look at it. So the whole idea of mean value theorem for integrals, you can see we have a function which is continuous. Let's say f over on a closed interval, then say there exists a point C in the open interval, so that the integral of that function over the interval AB, we divide by the length of the interval is f of c, where c is a point within the interval AB. So we are actually using that here to compute these probabilities. So we are saying if you can see the function we are talking about here. In the joint interval, we are talking about this function here. We are talking about this function here, which is an integral. The function in question is this integral. If you integrate over x, this function, and you put the limits of x, it will be a function of u. So we are talking here a function, this is a function of u. This definite integral of the joint with respect to x will be a function of u, because you will have integrated with respect to x and you put the limits for x, you can see it will be a function of u. So we are saying if this function is continuous at u equals to y, and also if f of yu is continuous at u equals to y, because essentially they are both functions, of u. F of yu is a function of u, and also this function is a function of u. So we are saying if this function is continuous at u equals to y, and if this f of yu is also continuous at u equals to y, then applying the mean value theorem, the MVD for integrals, we are actually saying integrate over the interval y minus h and y plus h. You know, actually y lies in that interval. Actually, y lies in that interval. So it's why we are integrating the function. This is the function in question over that interval y minus h to y plus h, like that. And you can see the length of that interval is 2h. You divide by the length of the interval will be the function evaluated at that value. The way you are saying the value will be the function evaluated at c. So it is the function evaluated at that value. Which value? Y. So you are actually evaluating this function at y. So when you evaluate this function at y,
Prof, why is it 2h and not h, 1 over h?
let me take you back. What is b minus a here? In the MVD for integrals, what is b minus a? I say this the length, isn't it? I want whoever has asked the question to respond so that I take you back
Okay,
there.
yeah,
Eh?
sure. Sure.
So we're in concurrence now.
Okay.
When you are here, what is the length of this interval? Y plus h minus y minus h. You are at home now?
Yes, I've seen it.
2h, yeah. So the whole idea is we are saying integrate the function. This is the function over the interval, and y is in that interval will be equals to the value of the function at that point, which is in the interval. So we are actually saying the value of this function at that point, which is in the interval. The point in the interval is y. So you are saying we evaluate this function at y. So you can actually see wherever there is u now, we have y. So you can actually see we have used the mean value theorem for integrals here. And similarly for the other one, it's the same story. The function in question is f of yu. So y lies in the interval y minus h, y plus h. So you integrate the function over the interval, divide by the length, evaluate the function at y, which is in the interval. You can see you're evaluating the function f of y of u at y, you get fy of y. So you can see we have actually used again mean value theorem for integrals here. So you are evaluating the numerator and the denominator using mean value theorem for integrals. And we have the results here. So therefore, we can now write what we have defined. We can now write what we have defined this result as probability that x lies in over the interval AB, given that y equals to y in the, so it is actually the limit as h tends to 0, which we have there. And then we also have this other result in the numerator. So we have just substituted in the numerator. Divide the numerator and denominator by 2h. Then I'll have that in the numerator, I'll have this in the denominator. And we already have the results now. This is what we are calling on the right-hand side. what we have on the right-hand side, also on the right-hand side, so we shall be having integral of f of x, y dx over marginal of y. You can now see here in this result, we no longer have h. So when you find the limit as a tend to 0, it is the same result. So provided f of y is not 0, that is actually when this is outside the support. So we are saying this is defined when f of y is positive, meaning in the support of the marginal. Outside the support, the whole, whatever we have, this probability will be taken to be 0. So the question of being undefined will not arise when we apply the mean value theorem for integrals. Now you can see the importance of calculus when studying probability also. Without calculus, you can't study even probability. Otherwise, things will just bog down. Now, with that explanation, we can thus extend the definition of conditional probability to continuous random variables as follows. Let x and y be continuous random variables having trained probability density function f of xy. The conditional probability density function of x given y is defined by, so you adapt now the way we were defining even for discrete, because we have already defined how we compute such, we have defined how we can compute such probabilities. So in a similar fashion, this is how we shall also be defining the conditional probability density function with the understanding of the explanation which we have used, so that we don't say what happens when probability of y equals to y, because y is continuous, because we are finding things in the limit. So you can actually see again for this conditional probability density function, you can see it is also non-negative. If you integrate over r, that is minus infinity to infinity. That means because it will be with respect to x. It will be with respect to x. So you can see, you know, the denominator is a function of y. So I'll be integrating the numerator with respect to x. And you can see when you integrate the joint with respect to x, you get the marginal of y. So you can see now you get the marginal of y with the marginal of y, you get 1. Meaning it is actually, whatever you have defined is actually a probability density function. So this is actually what they are calling the conditional PDF of x given y. This is a conditional BDF of x given y. You can see it integrates to 1. Now, suppose we define an event, say A, and we want to find the probability that x takes values in A, given that y equals to y, it means just integrate conditional BDF over that set A. For instance, suppose A is the interval AB. Then if I have to get that probability that x lies in AB, given that y equals to y, we just say integrate that function over AB, and you'll get the probability of interest. Similarly, you could have fixed x. You can talk of y given x. This is how it will be defined. And if you have to say, so we are talking about, so you can see that we are able to distinguish the two when we are talking of x given y. You can see here we are talking about, so it tells you the one which is being fixed, or which just a very just taken place, is actually to do with y. And then you can see the reverse when you are talking of y given x. Similarly, it's the other way around. It's just it's actually symmetric. So this is the case when you are talking about y, given that x equals to x. And for an event B, you want to compute over that y takes values in B, given that x has taken a small value x, integrate the conditional of y given x, now with respect to y, over that set. So in particular, suppose B is in that interval. So you just get the probability. The interval is CD, y lies in C, the interval CD. So you integrate the conditional over that interval. with respect to y, and you will get the probability of interest. We have an example here. X and y have a joint BDF 1 over 1 minus x. The support is 0 less than x less than y less than 1. I've indicated on the right hand side there. The shaded region is the support of this joint BDF. You can see I've drawn the line y equals x. You know, above the line y is greater than x, and below the line y is less than x, because you can see whether one is y greater than x, so you can see this is a shaded region. So it is not the unit square, no. It is that triangle there, this the shaded part, which is the support of this. So if you integrate, that's what I'm saying. If you integrate over the shaded region, you get 1. Or also you can integrate, you'll still be getting 1. You can see the limits, how they change. Here I'm saying dy dx, straightforward, you get y, but here I'm saying dx dy, you still be able to integrate and be able to show this 1. So it's a PDF over that whatever, over that shaded region. Now for the marginal of x, integrate the joint over y, and the limits of y is x to 1. X to 1, the join integrate with respect to y, you will get the result. This is the marginal of x. So having the marginal of x, we can get the conditional of y given x. You just need to define the join over the marginal. This is now the conditional of y given x. Similarly, you can get the marginal of y. Now to integrate, this is the marginal of y. And then you want to get the conditional of x given y, you get the join over the marginal, this conditional of x given y. And that is the support of that conditional density. All right. So remember, the one you see a minus here does not mean that it's negative. Remember, the values y lie in the less lie in the data for 0, 1. So the logarithm will be negative. So that is whatever you have here is always positive. So we have an exercise here for you. X and y have joined BDF. You need to identify the region, and then first verify that it's a BDF. F of xy is 2. The support is that the two random variables are positive or they are non-negative, and then must satisfy x plus y is less or equals to 1. Identify the region, get the limits, correct limits, and verify this a BDF, and then determine the conditional density of y given x, and also verify that is also a BDF. So integrate over y and see whether you will get 1. Integrate over y and see whether you will get 1. You will definitely get 1. When you have talked about the conditionals, what comes to mind is also the Bayes theorem. Remember, we discussed Bayes theorem in terms of events in a sample space, defined in the same sample space, but also we can also define Bayes theorem in terms of random variables, basically, or simply put, in terms of probability distributions. This is actually the general form of how actually Bayes theorem is actually applied in most cases in terms of distributions. In fact, when you talk of Bayesian statistics, it actually uses this idea of Bayes theorem. And even you shall see when you start the inference that we are actually using Bayes theorem. So we have defined the conditional density of x given y by this. This is our notation. The left-hand side is conditional of x given y. The numerator is the join. The denominator is the marginal. So basically, we are actually saying if you cross multiply the conditional and the marginal, you get the joint. So they are saying the chain is the conditional times the marginal. And you see, you can, when you have the join, you can get the marginal of x. Once you have the join, you can get the marginal of x and you can get the marginal of y. So you are saying the conditional of x given y is the join over the marginal of y. But remember also, the conditional of y given x is the join over the marginal of x. So when you want to get the conditional of x given y, which is a join of the join over the marginal of y, but also we remember that also the join is a conditional of y given x times the marginal of x. And the marginal of y, of course, we have seen that you integrate the join over x. So this join now, which is expressed as conditional of y given x times the marginal of x, I can now integrate it over x to get the marginal of y. So this is exactly what I've done. So you can see this is now what we call the marginal of y, whatever you have here. So actually this joint is what we have on the right hand side, and the marginal of y is what we have on the right hand side. So you have to get conditional of x given y. I'll just be using this over this. So that we have this. So the conditional, we are now saying the conditional density of x given y will be the conditional density of y given x times the marginal of x divided by actually the marginal of y. And the marginal of y is given by is actually by integrating the joint, which is the numerator, over x to get the marginal of y. So simply put, you can actually see whatever we are integrating here is actually the numerator. Whatever we are integrating here is actually the numerator. So you can see on the left-hand side, the concern is conditional of x given y. But you can see on the right-hand side, we have to use conditional of y given x and the marginal of x. This is the continuous version of the Bayes theorem. You can see if x and y are discrete random variables, we just need to have summation replaces integral. So instead of this integral, it will just be summation. And you can see because we are integrating the chain over x, that means for discrete, we are summing over x, you know, and we are allowed to write like this when they are discrete. We are allowed to write like this. You can say probability x equals to x given y equals to y. So this would be probability y equals to y given x equals to x times the marginal of x probability x equals to x, and then you sum the numerator over x. When they are discrete, you are allowed to write like this. And you can still adapt the same notations even for discrete, because basically, if you look at the whatever you have here, this is the same, this is exactly the notation. And you can see probability x equals to x is actually the marginal of x, which is actually that. And you can see this is actually the conditional of y given x, which is basically that. So they're basically the same. It is only that it is in the discrete fashion when you can relate the one we did for the events. Yeah? You can see it is a discrete fashion when you can compare or can relate to the one with the Bayes theorem for events. Remember, recall if we have events A1, A2 up to AK, which form a partition of the sample space S, then for any event A in S, so all these events, the K events plus this A, they are defined on the same sample space. So if we want to get the probability that A of AI given A will be probability of A given AI times probability of AI. And then you sum the numerator over I, over the events. All the K events, I equals 1 to K. You can see you can see that resemblance. You can see these are basically whatever you have here conditional are the conditional probabilities you are using. Well, these are actually the marginals. These are actually the marginals. And you can see we were summing over X. Eh? Now we are summing over all the events. It is some resemblance of the Bayes theorem in terms of events. So I wrote this in this fashion so that you can relate to this. And that's why I brought this remark so that you can go back and see what we meant. The Bayes theorem which we proved via the multiplication theorem, total probability theorem, and we proved the Bayes theorem in terms of events. We form a partition of the sample space. Now, after conditional distributions, another important aspect in probability theory is that of independence. We also talk about independent events. Now we want to bring about independent random variables. So formally, we study the notion of statistical independence of events. We now extend this notion to random variables. Random variables X and Y are said to be independent even only if, so we are saying even only if it's two-way, even only if the joint is the product of the marginals. And if the joint is the product of the marginals, it also means they're independent. That is, the joint probability distribution can be factorized into the marginal probability distribution. So if it is possible to factorize the joint into the marginal probability distributions, then the random variables in question are said to be statistically dependent. So from the definition of conditional probability, it follows that X and Y are independent. That means the conditional of X given Y will just be the marginal of X. Because to get the conditional of X given Y, you divide the joint by the marginal of Y. But the joint is the product. So if you divide them by the marginal of Y cancels, you remain with that. So the conditional of X given Y will be the marginal of X, and the conditional of Y given X will be the marginal of Y. So you can see it brings about when you are defining even independent events. Then you are talking about if you have two events which are independent, the occurrence or non-occurrence of the occurrence of one event is not influenced by occurrence or non-occurrence of the other event. So you can actually see the same concept. The same concept. In particular, for discrete X, we are allowed to write the chain probability as indicated here, probability that X equals to X, comma, Y equals to Y. Then we are actually saying the product of the marginals. What is how we can write the marginal of X. This is the marginal of Y. So we are actually saying the chain probability is equal to the product of the marginals. So what it actually means for discrete X, because we have seen for discrete X and Y, we can always present your probabilities in a table where inside the table we have the chain probabilities, and also we can get the marginals. If you sum over Y, you'll get the marginal of X, and if you sum over X, you'll get the marginal of Y. They all sum to 1. So we are actually, so basically we are actually saying when you multiply the marginal, you get the joint. So what it really means, I'll use an example here. X and Y, you can actually see in this general table here, you are saying this joint is actually you are multiplying the marginals as given here. The joint is the product of the marginals. So we are saying the probability which is here is actually as a product of what you have here and here of the marginals. So if you have got a value here, you have to multiply whatever you have here and here to get. For a value here, you multiply the one here and here, as seen in this example here. X and Y have joined and marginal distribution as indicated. So X takes values 1, 2, 3, Y takes values 1, 2, 3, 4. Those are the probabilities. The probabilities inside the table are the chain probabilities. These are the marginals of X. This is the marginal of X. So these are marginal probabilities. This is the marginal of Y. or sum to 1. If you check in the table, you will find that the chain probabilities are actually expressible as the product of the marginals. If you take for this one, 0.04 is a product of 0.2 and 0.2. If you check here, 0.125 is a product of 0.25 and 0.5. If you take here 0.12, it's a product of 0.4, 0.3, for all of them. That's what I'm saying. Actually, the joint probabilities go to product of the marginals for all xy, meaning the random variables in question here are independent. They are independent. So it should be for all possible values. If you find only one case which is not true, then they cannot be, you cannot deduce that they are independent. The second one is continuous case. We have the joint x positive, y positive. So this is defined in the first quadrant. So you get the marginal of x, integrate the joint over y. This is the integral over y. You get the result. You get the marginal of x. Take the exponential. Get the marginal of y. Integrate the joint over x. This is the same story. We get that. Another exponential. And you can see when you multiply the two, you actually get the joint. So this is an example of the case where the two random variables are actually independent. You multiply the marginals, you actually get the joint. So this is an example. So when with the continuous case where x and y are independent. Formally, when we discuss the random variables, the single random variable, we talk about its expectation or expected value. Now we have talked about bivariate distributions. Along with it, we must also discuss what we call bivariate expectation. So let x and y have a chain probability distribution f of x to y. Let u of xy be a function of x and y. So I've defined a function of the random variable. So it is also a random variable because we know a function of a random variable is a random variable, or a function of random variables is a random variable. So we can actually find its expected value. Then the expected value of this random variable, which is a function of x and y, is defined by this. So expectation of that. So to get the expectation of this random variable, because we are dealing with, we have to use a bivariate density. So basically the joint density. So you can see inside the integral is the value assumed by the random variable. The random variable is u of xy. You can see these are random. This is now the value assumed by that random variable. You can see here it is lowercase, lowercase. So you inside the integral, you have the value assumed. On the left-hand side is this random, so that the operator E, you say the expression is an operator, acts on random variables. So you'll integrate this with respect to x and y. You have that expectation. This now for continuous x. So for discrete x, integrals are replaced by summation. Now, also we talked about moments. We can also get uh, the moments of x and also the moments of y. When we are dealing with a single random variable, we talk about the moments of that random variable. And in particular, we discuss what you are calling the raw moments. We talk about the rth raw moment, which you are calling expected of x raised to r. That is the order of that moment. The expected of x is the mean. Is the mean of x. Then we have expected of x squared, expected of x cubed, expected of x raised to 4, and so forth. So we can also obtain the same, the moments for the individual random variables using the chain BDF. So the raw moments of X and Y are respectively. So you can see this was a notation for the raw moments of X. This is actually the Earth raw moment. So this is just a special case of what we have here. It's like we are saying U of XY is just X raised to R. U of XY is just, we have defined exactly X raised to R. So that is why I say X raised to R. So X raised to R, X raised to, so you just substitute here X raised to R, X raised to R, X raised to R, and you have the result here. But if I remember, if I integrate the chain over Y, I get the marginal of X. So if I integrate this chain over Y from minus infinity to infinity, I get this marginal of X. So I'll be having this integral, which is this one. I have X raised to R, and then the marginal of X dx. You can see things have now reduced to what you are dealing with when you are dealing with univariate case. It's like saying you can get using the chain, but you can see the same as when you are using the marginal of X. You get the moments of X. You can see this how we are dividing. Formerly, if you check, you are just saying X raised to R fx, because fx was the string of X. But now in this case, because we are starting to do simultaneously, this is the marginal of X. Similarly, we want to get the moments of Y, use a different notation for the order. Let's say Y raised to S. So we are actually, it's like we have defined U of XY to be just Y raised to S. And then the same goes. And you can see in this case, it goes back, you can actually generate them using the marginal of Y. In the univariate case now, goes back to univariate case, use the marginal of Y. So basically RNS are non-negative integers. They are non-negative, of course. When they take 0, it's just 1. And then of course the most important is when you have being positive integers, say 1 is the mean, 2 second moment, would you require the 2 for variance. Third moment, you will require also, in your academic say, the aspects of skewness, the fourth moment for kurtosis, and so forth. You can see in particular, the mean, we are going to use these notations for the means. The mean of X, formerly we were using mu for the mean generally. Now, because we have two random variables, we distinguish them. We are going to call mu X the mean of X, and mu Y. Mu X in the sense that mu subscript X the mean of X, and mu subscript Y the mean of Y. Remember also we did central moments. So central moments, they are moments about the mean. So in particular, again, when you want to get moments, central moments of X. So we have to get moments about the mean of X. So you can see this is X minus the mean of X raised to R. These are central moments of X. So you put there inside. So you are basically, it's like, okay, when you are saying you're just like the function U of XY is basically is defined as X minus mu X raised to R. So the same story follows. And then you reach here, you can now see it has now reduced the univariate case when you are using the marginal of X. Similarly, you can get the central moments for Y. So it will be about the mean of Y. Then you can see eventually again you'll be using the univariate case. You are again using the marginal of Y to get the moments. So these are the individual moments for the random variables, the raw moments and the central moments for the individual random variables, which you can actually see, you can actually get them using the marginals and get their individual moments. But we have now when you are dealing with bifurcate, there is another moment of importance which we call the chain moment, which require us to use the chain distribution. So we usually call this we have various names. We usually call it the chain moment. We also call it the product moment, or also we call them mixed moments. they all mean the same. Different books use different names, but they mean the same thing. You know. So when you talk about the origin, you see, even when you are talking about these raw moments are moments about the origin. Origin means mean equals zero. It's like saying raw moments are central moments about the origin, because central moments are moments about the mean. So when you take the mean to be zero, you get raw moments. So when you talk about mixed moments about the origin, mm, we define as expected. The way we now combine, there was just x raised to r. Now there's y raised to s, or x power r, y power s. There's a product. That's why we are saying product moment, or joint moment, or mixed moment. It's about the origin now. So you can see inside the integral. So this one you must use the joint PDF for continuous xy, or joint probability distribution in general. So you can see we are having here x raised to r, but lowercase inside the integral, y raised to s, y is lowercase, the join dx dy. So where r and s are non-negative integers. In particular, if r equals to s equals to 1, then we have, usually very important when computing the covariance. We require this when getting the covariance of the two random variables. So simply put, for discrete xy, summation replaces integral. Where you see integral, replace with summation of x and y, like that. Now, properties of bivariate expectation. Remember we also studied properties of expectation when you are dealing with univariate, just a single random variable. We also have similar properties here. So one, linearity. So suppose that x and y have a chain probability distribution f of x, y. Suppose we have defined a function of x and y. So this is a random variable, call it u. And then we have defined another function v, which is a function of x and y. So there are two functions of the two random variables. The functions are u and v. They are functions of x and y. So they are two random variables. Then for any constants a and b, so if I want to get expectation, you can see we have to find a linear function kind of these functions. A times u plus b times v. So it just the general property just says now you have a is a constant, will get outside. So E as an operator will only act on the random variable, which is u, as a function of y, of course, and then plus b and the expectation of the random variable, which is phi, as a function of y, of x and y, of course. So this is what we call the linearity property of expectation in the bivariate case. So where you have constants, just take them outside. Where you have now addition, just sum them up. Or even when you have subtraction, addition and subtraction, they go together. When you say a minus b, it's like saying a plus minus b, same story. Now, independence. You have said that if x and y are independent, the joint is factorizable as a product of the marginals. Also, this will also arise when x are independent. So if x and y are independent random variables, and then you have defined a random variable which is a function of x alone, and you have defined a random variable which is a function of y alone, and you want to get expectation of their product, will just be product of their expectations. So you can see whatever I have here, it is a function of x alone. The function u is a function of x alone. And the function v is a function of y alone. So when you want to get expression of such a product, you get as a product of expectations. This is a very important result. In particular, if x and y are independent, we said we have a very important which we require, this mixed moment here. When they are independent, you can see that for you to compute it, you need to use the joint. You need to use the joint. For you to compute this moment here, the mixed moment, when R equals S equals to 1, you will use the joint to get it. But if they are independent, this joint is factorizable as a product of the marginals, you know. So basically, it's like you are having a function of X alone and a function of Y alone. So it is actually a special case of this, basically. So it is a particular case. A function of X alone is X itself. A function of Y alone is Y itself. So we are actually saying exponent of X, Y, the product, is actually the product of expectations. So, so this is a result of independence. So it actually usually independence simplifies things. Eh? Usually when you talk of independence, actually independence simplifies what could seem complex or complicated. So even when simplifying problems, when you are dealing with independent random variables, you'll find they'll be similar. A very important inequality under these properties of bivariate expectation. We call it Cauchy squares inequality. This inequality says, remember again, when we define u of x, we are saying it is a function of x alone. When we define v of y, it's a function of y alone. So this Cauchy squares inequality says, if you get expectation of the product of u of x and v of y, remember u of x is a function of x alone, v of y is a function of y alone. If you get that expectation and you square the expectation, will always be less or equals to expectation of the square of the function u times expectation of the square of the function v. Remember, u is a function of x alone and v is a function of y alone. This is called Cauchy squares inequality. A special case of this inequality is actually when we take u of x to be x alone. You know, like the way we have found this special case, and this was a general case, we got a special case. We also want to write a special case of this Cauchy squares inequality. When u of x is x itself, phi of y is y itself. So we say expected of xy squared will always be less or equals to expected of x squared times expected of y squared. So we are actually saying the square of the mixed moment is less or equals to the product of the second row moments. Mm? Mm. And the mixed moment you are talking about is about the origin. Mm? Mm. The mixed moment, the square of the mixed moment about the origin is less or equals to the product of the second row moments. So, so we shall be using these properties as we proceed. Now, when studying two random variables, when we are studying one random variable, what was important was about its mean. It's a measure of dispersion, measures the center of the distribution. We also talk about variance. We measures what we call this dispersion. But when studying two random variables, we talk about what we call covariance. For the individual, we call it variance. But with the two random variables, we call them covariance. So we want to discuss covariance, and then we relate it to what we call the correlation. Now, an expectation of the form, because it is whatever you are having actually is a mixed moment here. or R is X is of order R, S, and the Y is of order S, and it's about AB. No, A is, you can see the is X minus A and Y minus B, meaning for constants A, B, we are talking about moments about AB. Mm. And you can see in particular, if A is equals to B equals 0, we are talking about AB being the origin, 0, 0. So we shall have X period of XR, YS, which we have already defined. Because whatever we define earlier is actually a special case, this one. So this is more general. So A is called a product moment. So this is a product moment, the general fashion of a product moment, or a mixed moment, or a chain moment. The one which you define up there was a special case. It was about the origin, which you have already defined. Now covariance. In a bifurcated distribution, the second order mixed moment is of particular importance. Second order mixed moment is of particular importance. So when you're talking about here x minus a, we are actually talking about deviations of observations x from a. And we are talking about deviations of observations y from b, you know. So we are saying in a bifurcated distribution, the second order mixed moment is of particular interest. So when you are talking about second order, when you are dealing with x alone, second order moment R will be 2. If you are dealing with y alone, second order moment S is 2. But when we are dealing with a mixed moment, second order moment means when you sum the powers, you get 2. Meaning when R is 1 and S is 1, you have a mixed second order moment. Now, and in particular, when we take deviations, not just about any arbitrary numbers A, B, if we take deviations about their means, okay, this is a particular case now. So I'm saying in a bifurcated distribution, the second order mixed moment is of particular importance. When the deviations are taken about the means, then we are saying let A be the mean of X and let B be the mean of Y. It is called the covariance of the distribution. Now we have defined, exactly we are saying it is a second order mixed moment and the deviations are taken about the means. Then we have what we call covariance of the distribution. Then we can now formally define what a covariance is. So covariance of X and Y. The covariance of X and Y denoted by, so we shall be calling it COF, the short form for covariance. So we say COF bracket or parenthesis X random variable X comma random variable Y. This now say covariance of X and Y. This is notation. Now, this defined as given on the right-hand side. What we have just said here. Second order mixed moment, meaning R equals to S equals to 1, and the deviations are about their means. So you can actually see here, R is 1, S is 1, A is mu X, as indicated here, B is mu Y, is indicated here, because we have said mu X is the mean of X and mu Y is the mean of Y. So we have actually defined covariance. Now, you see also for the individual random variables, each one has got, as we have seen, we are using the mu X for the mean of X, mu Y for the mean of Y. Also, we have their corresponding variances. We shall use sigma X squared to denote variance of X. We shall use sigma Y squared to denote var of Y. So if our X and var of Y are finite, then the expectation defined above exists. If the two random variables are finite variances, then this covariance we have defined will exist. That means that covariance, and that covariance is actually finite. Now you'll see that you can see that if you replace y by x, you'll get cof xx. You replace y by x, you get cof xx. So this will y will become x, and this mu y becomes mu x. So I'll be getting here x minus mu x squared, which gives me var x, meaning cof xx is var x, which is actually sigma x squared. So also we took of cof y is var y, with sigma y squared. So this will suggest the following notation, because we already have a notation for a variance. For var x, we are calling with sigma x squared. For var y, we are calling it sigma y squared. Then we can have this notation to denote the covariance of x and y. Just say sigma xy. We shall use it sigma xy to denote covariance of x and y. So that in our notation, when we write sigma xx, will be cof xx, which is sigma x squared. So in our usage, this notation, sigma xx is just sigma x squared. Very well. Covariance, what is covariance? So we have said variance is, we should say, exactly a measure of variation. How far are the observations from the center of the distribution? How about covariance? You see, covariance is a measure of covariation of x and y. It indicates the degree of association between the random variables. If x tends to be large when y is large and small when y is small, then the covariance will be positive. That means for large x, y will tend to be large. And for small x, y will be tend to be small. Then the covariance will be positive. If large values of x tend to be correspond to small values of y, the covariance will be negative. So when you say large values of x tend to correspond to small values of y, it means small values of x will correspond to large values of y. Same story. So in that case, the covariance will be negative. So it tells us how the two variables are associated. If there is no such tendency, the covariance will be zero. They have no association. The covariance will be zero. So it actually tells you when you are talking about independence, when you say the independence, it actually means none of variables have no association. In such a case, we should expect their covariance to be zero for independent nano variables. They have no association. We shall see. Now, we know that now if we expand, we can get a formula for getting covariance. We have defined by our definition here. If we expand the right-hand side and we use linearity properties of expectation, just multiply this out, expand, x minus mu x times y minus mu y, and then you take expectation. Is exactly what I've done here. I've expanded. I'm taking expectation here. And then I simplify. I get this result. After you simplify that line, you get this line here, you get that stuff. It's a very straightforward thing. So we are actually saying we have found a formula which you can really use to get the covariance between two random variables x and y. It's basically what? Covariance between x and y is actually the mixed moment minus the product of their means. So this is actually a more convenient formula for computing covariance of x and y. You can actually see that if you replace y by x, you get of xx, which is for x, and you can see this one becomes exponent of x squared. This one becomes exponent of x all squared. Give you the formula for variance. It was a special case. It gives you the formula for variance. What goes together with variance is what you call correlation. Usually, you find that covariance is actually affected by the units of measurement. It's affected by the units of measurement. But we want to look at a measure which is not affected by the units of measurement. So let us talk about correlation. So the covariance is not a good measure of association in that it is affected by change in scale or measurement. So when you change the scale, covariance will change. For example, if x and y are measured in centimeters, the covariance would be 100 times what it would be if they were measured in meters. You change the scale. So to obtain a measure of association which is inferent to change in scale, we use the coefficient of correlation. So to lead us now, this will be kind of standardized in such a way that it will not be affected by change in scale. So correlation between x and y. So the correlation between x and y is denoted. We shall use the notation CORR to denote correlation of x and y. So when you are saying x and y, you replace them with a comma. You separate them with a comma, I mean, and it's defined by, so this is our notation. It's actually covariance over the square root of the product of their variances. This is the formula for correlation, which is further denoted by rho xy. Just to adapt this notation, which you are calling it a covariance sigma xy, we shall use this notation to denote correlation, rho xy. This is a Greek letter rho. Use a Greek letter rho. So using our notation here, rho xy, this Greek letter subscripts, the way we were writing for sigma xy, x and y are subscripts to denote cof xy. So we are just saying for correlation, we are saying rho xy is correlation xy, same story. Just a minute. So now we talk about covariance being positive, being negative, being zero. So usually when it comes to the sign of the correlation is actually the sign of the covariance. So whatever in the denominator, we usually get this square root, we take a positive root in the denominator. Variance is always positive. So we are talking about positive, but when getting also square root, we take a positive root in the denominator. So you'll find that the sign of the correlation will be the sign of the covariance. Now to simplify things, we have indicated we have a notation for the correlation. So rho xy, Greek letter rho. You have the Greek alphabet. So you are going to say rho xy equals to sigma xy divide, that is now the correlation covariance square root of the variances. Remember, this is variance of x, variance of y. Now, you have this notation So you can see if you get the square root of sigma x squared, standard deviation, sigma x, and sigma y, standard deviation of x, standard deviation of y. So it's actually, so rho xy is sigma xy, which is covariance, over the product of standard deviations. So rho xy is called the coefficient of correlation, or correlation coefficient. It doesn't matter how you say it. It's called the coefficient of correlation, or simply correlation coefficient between x and y. Now I want to use the Cauchy's Squares inequality. You see, the Cauchy's Squares inequality was saying a spread of this, the square of the expectation of u, that means v, is that equals to expectation of product of the expectation of the squares. So if we use Cauchy's Squares inequality here, if I use Cauchy's Squares inequality, but now I'm taking these moments about the means. I'm taking moments about the means. I'll say the mixed moment about the means, the square of the mixed moment about the means will be less or equals to expectation of the squares about the means. This is called the squares. The square of the mixed moment will always be less than or equals to expectation of the squares. This is called the squares inequality. But whatever I have here, you can see this is actually our covariance. This covariance between x and y. So I'm saying covariance squared is less or equals to, but you can see whatever I have here is far of x. Whatever I have here is far of y. So you are saying the square of covariance will always be less or equals to the product of the variances. Now we are using cov xy, the notation is sigma xy. So square it. So sigma xy squared will always be less or equals to, for x is sigma x squared, for y is sigma y squared. If I divide both sides by the variances on the right-hand side, I'll get 1 on the right-hand side, and the left-hand side becomes sigma xy squared over sigma x squared, sigma y squared. And if you relate, you can see what we are calling rho xy. Rho xy is sigma xy divided by sigma x times sigma y. So you can see whatever I have now here, if this is rho xy, is sigma xy over sigma x times sigma y, whatever I have here, you can actually see this is rho xy squared. So it says rho xy squared is less or equals to 1. So it means all the time, rho xy squared will always be less or equals to 1. What it actually means, rho xy itself lies between -1 and 1. If rho xy squared is always less or equals to 1, it means the correlation lies between -1 and 1. 1 and 1 inclusive. So we have said the sign of the covariance will be the sign of the correlation. So if the correlation is positive, it means we had a positive covariance. If the correlation is negative, it means we had a negative covariance. And if the correlation is 0, that means we had 0 covariance. Now, if the correlation is positive, then x and y are said to be positively correlated. While if rho xy is negative, then they are said to be negatively correlated. If rho xy is 0, x and y are said to be uncorrelated. We know that the correlation is 0 even only if the covariance is 0. The sign of the correlation is determined by the sign of covariance. So here are the examples. X and Y have joined and marginal distributions indicated below. This for discrete. So these possible values of X 0, 1, 3, possible values of Y 0, 1, 2. These are the joint probabilities, marginal of X, marginal of Y. So given this information, one can get the mean of X, the second moment of X, just using the marginals. Bar of X, use the marginal. Similarly for Y, get the mean of X, the second moment, get the fair of Y. Get the mixed moment now. You have to use the chain probabilities. You get the mixed moment. Get the covariance using the formula. So the moment you see a minus, the correlation will be a minus. Get the correlation. You can see the covariance is a minus over square root of. This is variance of X, this is variance of Y. Then you have the correlation, minus 0.16. So you can actually, by looking at the magnitude, you can actually tell the strength. Because it lies between -1 and 1, you can tell the strength, whether it is very strong correlation or very small correlation. As you move towards 1, you are talking about being strong, in the positive direction. And also can be strong in the negative direction when you move towards -1. As you move towards 0, from the right or from the left, you are having a very weak correlation. That was a discrete case. For the continuous case, we have that. So we can again get the mean of X, get the second moments, because of, if I give you have, the second is this is a bit symmetric. If I give you have the mean of Y, you have the mean of X. So that you can see symmetric. The second moments, they are the same, they are equal. So square root of X will be the same as square root of Y, square root of X squared will be square root of Y squared, power of X just the same as power of Y. Now get the square root of XY, that get covariance, get correlation. You see, this is a very weak one. Negatively, they are both negatively. It's a bit stronger than this one, but they are both negatively correlated. Properties of covariance and correlation. That one of independence. If X and Y are independent, random variables with finite variances, then a spread of XY, we have talked about this. We know the mixed moment is a product of the means, and hence you'll find that from the formula of covariance now, is a mixed minus product of the means will be 0 because the two now are equal. So when random variables are dependent, their covariance is actually 0. And then because we have said the sign of the correlation is determined by covariance, so when covariance is 0, a correlation is 0. Basically, independent random variables are uncorrelated. But there's a catch here. However, the converse is not true. That is, when the correlation is 0, does not necessarily imply independence. So we don't deduce that random variables are independent when the correlation is 0. We can have random variables which have correlation 0 and yet they are not independent, they are dependent. Thus, two dependent random variables can be uncorrelated. There exist such random variables. So also, we know random variables which are independent, their covariance is 0. But you cannot deduce that when you find covariance being 0, you cannot deduce that they are independent. You can have random variables which have covariance equals 0, yet they are dependent. You find their covariance 0, but you'll find that their join is not factorizable as product of the marginals. Actually, that is the stronger definition of independence is basically based on the margin, on the join being factorized as a product of the marginals. Linear relationship. You also, when you're looking also the when you are studying variance, we talk about variance of a linear function. And we saw that variance is translation invariant, but changes with scale. Let's see what happens here. Suppose that x is a random variable with finite variance sigma x squared, and suppose that y equals to ax plus b. So we have defined y as a linear function of x. A and b are constants here. And in particular, a is not 0. Then you can have the mean of y using the linear properties of expectation. So mu of y, our notation, expected of y, linear properties, just be a times square root of x plus b, but square root of x is mu x. Now let us get also variance of y notation, sigma y squared. These are var of y. Remember, how we work at the variance for linear function, we need to square the scale parameter a squared var x, a squared sigma x squared. That's why we were saying variance is translation invariant. That's why it's not a function of b, it's translation invariant, but changes with scale, but it's not scale invariant. If we look, so we want to find the covariance. Covariance of x and y is cov xy. This is how we define covariance up there. So we have x minus mu x, and then when it comes to y minus mu y, get now y minus mu y. Our y is ax plus b, and mu y is a mu x plus b. So when you get y minus mu y, b and b will cancel. You remain with, so you get ax minus a mu x. That's why you see ax minus a mu x. You can see, you can factor out a. You can factor out a because a constant, and then whatever you have now a square. X minus mu x and x minus mu x becomes x minus mu x squared. But you can see by definition, this is variance of x. So this sigma x squared. So actually the covariance between x and y, in the case when y is a linear function of x, it's like you want to look at how is y and x associated. Y covariance between x and y is actually a times variance of x. So the covariance between x and y is actually a times variance of x when y is a linear function of x in that manner. Now, we have to get the standard deviation. Standard deviation of y is the square root of variance of y. But variance of y is a squared sigma x squared. So we take the square root. Of course, square root of sigma x squared is standard deviation, sigma x. But now, when we want to get the square root of a squared, we write it as mod a. Because standard deviation here is taken to be positive. So in general, standard deviation of x is taken to be positive. Standard deviation of y is taken to be positive. But you see, our constant a might be negative. So you say if a is negative, if you square it, you get a squared. So we write it as mod a sigma x. So when getting here, we write it as mod a. Where mod a, so that we ensure that sigma y is positive. If a is positive, it will just be a. But if a is negative, this mod a is minus a. So that will ensure that our sigma y is positive. You can see what we have to go to. We are not about to break the rules. We have said standard deviation is always taken to be positive. It is never negative. So that is how we write. So mod a, so that if a is positive, there'll just be a. But if a was negative in our definition here, they were just say a is a constant. If a is positive, and you have said specifically A is not 0. So A can be positive or negative. So if A is positive, we shall just be calling it A, and it will be positive. If A is negative, then this mode A is called minus A. So that is also positive to guarantee that our standard deviation is positive. Now, therefore, let us see correlation. Correlation is covariance divided by the product of standard deviations. Now, covariance we have found to be covariance between x and y, we have found to be A times the variance of x, which is sigma x squared. Put it there. That is the covariance. Now, put here, so we have here the standard deviation of x, which is sigma x, times standard deviation of y, which we have here. Standard deviation of y here, we are having it in terms of standard deviation of x. This mode A sigma x, that is standard deviation of y. So we have here standard deviation of x, which is sigma x, and standard deviation of y, which is mode A sigma x. So that's why you are having here mode A sigma x squared. So sigma x is here, sigma x is here. So this mode A sigma x squared. Now sigma x squared and sigma x squared cancel. You have correlation is actually A over mode A. So the sign, so we have said if A is positive, if A is positive, mode A is A. Hmm? If A is positive, this mode A is A. So A over A will be 1. So correlation will be 1 when A is positive. And if A is negative, this mode A is minus A. So A over minus A is minus 1. So correlation will be 1 when A is positive and minus 1 when A is negative. So when you divide the linear function, if this A is positive, the correlation between x and y will be 1. And if A is negative, the correlation between x and y is minus 1. So the value of the correlation provides a measure of the extent to which two random variables x and y are linearly related. How are they linearly related? Because we are defining the linear function. So if the joint distribution of x and y is relatively concentrated around a straight line, so when you really have, when you say they are linearly related, if you are to plot these values, they will fall on a straight line with positive gradient. They will have a correlation of 1, you know. And if they fall on a straight line with negative gradient, they will have a correlation of minus 1. Because we're talking about linear relationship. So if the joint, you know, all these aspects is about joint distribution. So if the joint distribution of x and y is relatively concentrated around a straight line in the xy plane, that has a positive slope, then the correlation would typically be close to 1. So if you are to plot data, what you actually call the scatter plot, you find it's almost following a straight line, then you know, you're seeing as almost following that scatter plot is almost like a straight line, with positive slope, then you know the correlation will be very close to 1. Mm? If the joint distribution is really concentrated around a straight line that has a negative slope, then you'll find that they will be typically close to be minus 1. So you can always, when you visualize, even in when you are studying distributions and you have data, you can always interpret by visualizing using scatter plots. Like in R, where we usually see the shiny apps. So so when we are talking about actually plus or minus 1, we are talking about in this analysis, when we are talking about correlation being plus or minus 1, we are talking about perfect linear relationship. It's perfect. That is why if you are to plot values with a perfect linear relationship, they will actually fall on a straight line. Mm. If A is positive, that correlation will be 1. If A is negative, that correlation will be -1. Straight line, either with a positive slope or negative slope. So what we actually call when you with positive slope is what you usually call the direct relationship, and with negative slope we call inverse relationship. Direct relationship means large values of x will correspond to large values of y. Inverse relationship will mean large values of x will correspond to small values of y. Inverse relationship. So even when you are saying, it may not be when you can draw conclusions that if you draw you have a scatter diagram. If they are just concentrated around a straight line, you can actually see that's some direct relationship. It is concentrated around a straight line with positive slope. You can actually make conclusion and talk of a direct relationship there. Of course, when you are dealing with data, you don't expect perfect relationship because in analysis with data, you don't get that perfect relationship unless you had data actually drawn from a particular known model. But if you are actually having data which was just collected in the field there, you may not really capture, but you can always draw conclusions whether you have some direct relationship or some inverse relationship. Mm. Variance of a sum or difference. Mm. Suppose that x and y are enough variables to definite variances, then suppose you want to get variance of x plus y or x minus y will be var of x plus var of y. So when getting variance of a sum or difference, you always sum the variances, whether you are subtracting or adding. Var of x plus y is var x plus var y. Var of x minus y is var x plus y. Where you only differ is the covariance. When this is a plus, you say plus twice cov xy. And when this is a minus, you say minus twice cov xy. But you can see when they are independent, and x and y are independent, this covariance is 0. So when they are independent, variance of x plus y is the same as var of x minus y. You just sum their variances. For any constants a and b, suppose I want to find cov ax and by, covariance between ax and by, where a and b are constants. It is actually found as ab cov xy. Constants just get outside the covariance. It's actually ab of xy. Now, if I want to get, you have defined a linear function of x and y, say ax plus or minus by, and you want to get the variance, the same story. A squared for x plus b squared for y plus or minus. So you can actually, when you are talking about plus or minus, you'll be saying cov ax by, which is here. So it is twice 2ab of xy. And if x and y are independent, var of ax plus or minus by is actually a squared for x plus b squared for y. Doesn't matter now because they only differ in the covariance. Now, because when we are talking about bivariate statistics, I said the same concepts can be extended to bivariate 3. We can extend them to 4. But when we are dealing with many, we usually have better ways of expressing our variances. We have better ways of expressing our variances in terms of, so we are talking about, when you have got more than one variable, you're talking about 2, 3, what is at play there are the variances of those variables and their covariances. So when it comes to about the dispersion or the variation, or you want to talk, so you'll be talking about the variation and also the covariation of those random variables. You are talking about the variation, that means variances for the individual random variables and covariation. So when it comes to talking about variation for the with respect to individual random variables, you are going to capture them using their variances. And when you are talking about the covariation of the random variables, now pairwise, covariation between any two of them, you are going to capture using covariance. So there are two aspects here, variances and covariances. So there's a way of expressing, for instance, if I want, like the way I've said here, okay, we have said, look at this general one here. We have said far of ax, secondly, linear function of x and y. Let I've taken the case for the plus. Far of ax plus by is equals to a squared for x plus b squared for y plus twice ab of xy. So I pick that one here. You can see whatever, so we know the result on the right hand side, but you can actually see whatever I have on the left hand side, I can rewrite as follows. See this ax plus by, I can write this ab, this row vector having the elements a and b, and this column vector having the elements x, y. There are no variables. So this is actually, we call it now a random vector. This is a random vector, two-dimensional random vector. Now, if you see the result on the right hand side, the result on the right hand side can be expressed using matrices, using these matrix and these vectors. If I write say this row vector AB, so I multiply this matrix with row vector AB and post multiply with this column vector AB, and the matrix I have here along the diagonal are the variances for x and for y. Of the diagonal are the covariances. This is cov xy and this is cov yx, but the two are equal. If you say covariance of x and y, it's just the same as cov y, covariance of y and x. Meaning we are dealing with a matrix which we say the symmetric. Symmetric in the sense that you can reflect it along the leading diagonal. That we have the upper triangular matrix and lower triangular matrix are just but the same. Now, if you expand this, go and expand this. If you expand this, you will get what you have on the right hand side. For the case of a plus, you will have what you have in the right hand side. So we usually call this matrix, we usually denote it, we call it dispersion matrix. Dispersion matrix, the elements are the variances and covariances. That's what I was saying when you are studying more than one random variable. Of interest are the variations and covariations. So we usually capture those, the variation and covariation using this matrix. We usually denote it by Greek letter uppercase sigma. So this matrix, we call it sigma, which usually used for summation, but in this context, we use it to denote that matrix so that we call it dispersion matrix or covariance matrix. So if you see my notation, we can see whatever you have here is the variance of x, this is the variance of y. You can actually see my notation. This is sigma x squared, sigma y squared. Here is sigma xy, the covariance, and this is sigma yx. But you see, cov xy is cov yx. So sigma xy is sigma yx. So it's symmetric. So you say this matrix is symmetric. So usually it has got also other properties that usually this matrix is positive definite. And for I don't want to go into positive definiteness in algebra about of a matrix. There's its own definition, but more importantly, for your case, when you hear of a positive definite matrix, such matrices have got positive determinant. In other words, and you know, for a matrix having a positive determinant, you can always find an inverse. Now, so we call this matrix covariance matrix or dispersion matrix. So the elements, you can see, there are variances and covariances. Why is it called covariance? Sometimes people call it variance covariance matrix, but I don't like it that way because I know variance is a special case of covariance. So when you say variance covariance matrix, you are just basically repeating. It suffices just say it's a covariance matrix because these covariances that you see here, this is cov XX, this is cov YY. So they are all covariances anyway. So I don't like calling it variance. I like just calling it covariance matrix or simply dispersion matrix. So when we are for a single random variable, you talk about variance of a random variable. Like you say, we have a random variable x, you say far off a random variable x. Or you have a random variable y, you say variance of a random variable y. But when we are having more than one random variable, like for in this case, two, we just say we need a covariance matrix of the random vector. Now, this you say this is whatever you have is a random vector of dimension 2. Hmm? This is a random vector. So we call this covariance matrix of the random vector, but these are all covariances, or simply put, the dispersion matrix. So you can actually see, because see, this matrix we have here is of dimension 2, because the random vector in question is of dimension 2, or two-dimensional for that matter. So when you have got, say, how many random variables can I say? Suppose you have got n random variables. Then you are talking about your dispersion matrix being of dimension n. It will be a square matrix of dimension n. So you have got 3, it will be 3 by 3 square matrix of dimension 3. We have got 4 square matrix of dimension. And in general, they are all symmetric matrices. They are positive definite. Now, we have talked about conditional distributions. So associated with it should also be conditional expectations, because we have got the distribution. It has got its mean, it has got its variance. So if we have got a conditional distribution, it must have its mean and its variance, which we now call conditional expectation and conditional variance. Already we know the notation we use for expectation, like for x, we just say expected of x. Now, the conditional expectation of y given x. Now, this is a notation. The random variable y given x is denoted by this. Expectation y given x. When you see this vertical line, we read it to be given. And it's defined to be a function of the random variable x. So this is actually a function of the random variable x. You see, when we are taking expectation of y given x, it is actually averaging over y for given x. So essentially, this operator is acting on y for given x. So essentially, whatever you'll be having, the result will be a function of the random variable x. You can see again, this is a random variable now. This expectation is a function of the random variable x. So this expectation is a random variable. So that's what I'm saying, is defined to be a function of the random variable x, whose value is this. So this random variable will assume this value. So this is a function of x, is a random variable, and the value it will assume is this one now. Exponent of y given small x. Now this value, the value it assumes, is now defined as follows. Exponent of y given small x. Inside the intercrot, we are now assuming this continuous. Of course, this is for discrete. So you multiply by y and you use the conditional. You're going to hear this conditional of y given x. Now we need to use the conditional distribution of y given x, and then you integrate with respect to y. You can actually see in this integral, essentially, it will actually be a function of small x eventually. So this is what you do for continuous x. For discrete x and y, you summation replaces integral. Now, The value of this is not defined for any value of x for which the marginal is equal to 0. However, since these values of x form a set of points whose probability is 0, the definition of it at such a point is relevant. Which is actually outside the support. What is outside the support, we cannot talk of expression of y given s at such a point. It's outside the support. Now, similarly, we can also do the same for the variance. For any value of small x, let var y given x be the variance of the conditional distribution of y given that x equals x. You know, then var of y given x is defined as follows. So it will follow the same formula as before. It's only that it's now conditional on x. The way if you wanted var of y will be exponent of y squared minus the square of exponent of y. But the same formula, you are now talking about var of y given x, exponent of y squared given x, minus the square of exponent of y given x. I now say the conditional variance of y given x is the second moment of y given x minus the mean, the square of the mean of y given x. As simple as that. This is now what we call the conditional variance of y, given that the random variable has assumed the value small x. The way you are calling it here, the mean of y given x. So the notation again is just the same story. See, var of y given x is the conditional variance. The way you are saying this is conditional expectation. And when you talk of conditional expectation, we can also, when you are talking about this, is just like saying also the conditional mean, because you are saying expected of x can also be called the mean of x. So when you say expected of y given x, we can call a conditional expression of y given x. So similarly, we can define for x given y. And then we talk about conditional variance of x given y. Let us see here, example. X and y have joined BDF. So if we integrate over the support, you should be able to get one. We are getting the marginal. This is the marginal of x. Integrate the join over y. The limits of y is equal to x. You get here. This is the marginal of x. This is the conditional of y given x. The joined over the marginal. You have gotten here the conditional. That is the support. Is a conditional of y given x. Now, if I want to get expected of y given x, you get the limits of y. The limits of y is 0 to x, multiply by y, and then you use this conditional distribution. Then you integrate with respect to y. Put the limits, you have the result. That's why you see now this is a function of x. You know, the expected of y given x is a function of x, where x lies in the interval 0, 1. That's why I was saying given that was essentially it will be a function of x. We have to get the second moment, same story. But now here, y squared. The rest remain the same. Get the square of y squared given x, x squared over 2. And x lies in interval 0, 1. From the formula, you can get your var of y given x. This is a function of x, x squared over 18. X lies in interval 0, 1. So this is a conditional mean. This is now what you can call conditional mean of x of y given x. This conditional variance of y given x. They are functions of x. What do I meant before? That when you say expected of y given the random variable is a random variable. So if I say expected of y given capital X, it will be 2 over 3 capital X. That is what you are calling now a random variable. When here is capital, now this is capital here. So this is now a random variable, which will assume this value. Properties of conditional expectation and variance. There are two important properties with respect to conditional expectation and variance, and usually they are used in Bayesian statistics. Bayesian statistics is also where we apply the Bayes theorem. Together with these properties of conditional expectation and variance. The first one says expected of y given x is expected of y. So let us look at that first. Let us not even talk about the second one. The first one says expected of y given x is expected of y. On the right hand side is obvious to us. It says the mean of y. But the left hand side says, let me start by saying, you remember when we were saying expected of y given x, we said it is a function of x, the random factor. That's what we're saying. This one, look at my cursor here. Expected of y given x is a function of the random variable x. It is random. That is why this other operator e is now acting on it. So the first one acts on y for given x. Now the resultant is a random variable which is a function of x, and then the second e acts on it. So the first is averaging of y is averaging over y for given x, and then now the second one averages over x. So it says when you do that, it is the same as just saying averaging over y, the mean of y. So it says the mean of y is the right hand side, or let me just start with the left hand side. The mean of the conditional mean of y given x is the mean of y. Because we agreed to say expectation is just as we say the mean. So the mean of the conditional mean, here is the conditional mean of y given x. Then we now talk about the mean of that. So the mean of the conditional mean of y given x is just the mean of y. And we can actually prove it here. We have said expected of y given x, this one is random variable, which assumes this value. Okay, so it assumes this value. You can see it's a function of x. So when this one is coming to average over it, it's going to be averaging over x now with respect to the marginal of x. This is what it actually means. I'm assuming we are dealing with continuous. We are using discrete. You just need to sum. So don't bother. Don't worry. So expected of y given x. So you look at this first. This is another variable which takes this value. Given x. You can actually see what you are doing here. You can see you put y, conditional of y given x respect to y. So expected of y given x, you can see I'm inside this parenthesis here. I integrate, I have to put y. I have to use conditional of y given x, integrate respect to y. So I have now to set what that result is. That's even what we did in this example here. We say minus infinity to infinity because, when you define the density, you say it's zero otherwise. So you likely go to your support directly. Now, so you have that integral, then you have the marginal, you have dx there. Now let us look at this. We want to look at this. You see here, it's like we have an integral here with respect to y. Okay? And then I multiply by the marginal, and then I integrate with respect to x. But you can see this same integral, I can decide to integrate with respect to x first and then y. So if I'll do with respect to x first, I have to put those functions having x. So this conditional will be having x, and the marginal of x will be having x. I integrate that with respect to x. But remember also, this one now will be having y eventually. It will be now combined with this y, which is outside here, and then everything I now integrate with respect to y. If you come here, this is the this is now the conditional of y given x times the marginal of x. Remember what we saw earlier? The conditional of y given x times the marginal of x gives you the joint. You know, so this conditional of y given x times the marginal will give me the joint of x and y. You can see the way our notations. So it's like now I'm integrating the joint over x. But if you integrate the joint over x, you get the marginal of y. So this integral in this parenthesis here is actually the marginal of y. Look at our notation, fy of y. So I'm having here integral now. Whatever we are calling will be a function of y is here. It will be exactly the marginal of y multiplied by y. This is a marginal of y integrates back to y. But by definition, this is expected of y. So expected of y given x is just expected of y. And this property also usually helps us in simplifying. So we're actually saying that the mean of the casual mean of y given x is the mean of y. In this proof, we have assumed that we are dealing with discrete continuous variables. For discrete, you just replace integral by summation, so it doesn't matter. We don't have to redo. As a remark, suppose we are talking about a mixed moment given x. If you look at here, expected of xy given x. You see, if we are looking at the expected of xy given x, as far as this expectation is concerned, because x is given, this would just come and act on y given x. X can come outside here. That is why you see my x here can come out here because it is given. So it will come out here, and then this will come and act on it. So what this will act on it only will be y for given x, and then each x will comes out, and then you will combine with the result of here, which will be a function of x. So everything will be a function of x here, and then this one averages over x. So the two are the same. So expected of xy given x is just expected of x times expected of y given x. So it's a consequence of that result also. But using again, we have said expected of xy given x is just expectation of what you have here. The way we have used the result, this expected of y given x is just expected of this. So we can deduce from there that expected of xy given x is just expected of this. With this one. So expected of xy given x is just expected of it's actually the mixed moment. Expected of xy given x is just the mixed moment expected of xy. And because it's equals to this on the right hand side, so the mixed moment can just be expressed as expected of x times expected of y given x. Those are the two that say. That is number one. Number two. Number two says, this is now number one was just about the means. The conditional mean of y given x. These are talking about conditional variance of y given x. And actually says we have seen that this is a conditional mean of y given x. Because a function of the random variable x, we can find its variance. And also we have var of y given x is a function of the random variable x. So we can actually find its expectation also. So whatever we have here, they are random variables. These are random variable. Var of y given x is a function of the random variable x. Exponent of y given x is a function of the random variable. So they are random variable. So we can find variance of a random variable x, and we can find expectation of a random variable x. A function of a random variable x, that is. So it actually says expected of the conditional variance of y given x plus var of the conditional mean of y given x is just var of y. So the first is about conditional expectation, which is about the conditional mean. And also the second one is about conditional variance. So this is now, these are conditional expectation, this conditional variance. And it relates to the mean and variance of y alone. So we have seen property number one. Property number two, so straightforward. We have said when you want to find variance, conditional variance, you can see the way you are finding here. You wanted to get conditional variance, you just have to use this formula here. Var of y given x is a bit of y squared given x times the square of x of y given x. That's a formula for conditional variance. The way it's just like the ordinary variance, you just need to condition on the given variable. Now, so if we want to do that, we just realize that var of y given x is x squared of y squared given x minus the square of x squared of y given x. Now, as I've indicated, var of y given the random variable is a function of the random variable x. So we can find its expectation. This is a function of the random variable x. That's why this operator E will act on it because it's a function of a random variable x. Now, if var of y given small x is given like that on the right hand side using the formula, then var of y given uppercase x follows the same formula. You only need to have this uppercase. So var of y given small x, that one. Var of y given capital X, this random variable is the same. You can see the same story. Expected of y squared given x. We can actually see here expected of y given x capital, 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 small, small, small. We are just making it random here so that our operator can act on it. So I'll write this using whatever I have there. And then now I want to take expectations so that I see what will I get. Because if you see here, I'm doing expectation of r of y given x. And you can see in 2, it's actually that one. I'm talking about expectation of r of y given x. So what is that? Hmm? So expectation of r of y given x, now we come and act on it. So this E is just acting on here when each one has been put capital, 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 which is here, here, here. So this expectation now acts on it. So we have expected of y squared given x, and then this expectation now is this one. The linearity property, this expectation again is this one. That we have expected of y given capital X. Now this is squared. The expectation of the square. But this expectation of this. And then here we use what we approved in 1. You know, expected of y given x is expected of x. Meaning expected of y squared given x will just be expected of y squared. So I've simplified this using 1. You see I'm negating here from 1. We have proved that result. expected of y given x, meaning expected of y squared given x will just be expected of y squared. We are using 1 here, not directly, but the idea. And then here, expected of y given x, and then square it, the expectation, so it is the way it is up there. So it is here where we have used 1. In the second line, you can see this part is here. This part is here. In between here, I've just subtracted the mean of what the square of the mean, and because it's not there, I've cancelled it by adding. So this one is this one. This one is this one. I subtract the square of the mean of y, and I add the square of the mean of y. So this will cancel. So I have not changed anything. But when I do that, should be able to observe that whatever I have here, I have variance of y because it's the second moment minus the square of the mean. So this is actually far of y. This is far of y. And then I factor out a minus here. I want to factor out a minus here. So I have minus. So I'll be having expectation of this minus this. Factor out the minus. Yeah. So I have this result. So I'll be having this one coming here, and then I have this one coming here with a minus. If you open the brackets, you'll go back there. I want to use 1 again. Forget about far of y. We have it. We are just writing it. We're just putting it as it was there. And then if you come here, you can actually see I'm using 1 again here in reverse. Expected of y is expected of y given x, the one we approved. So here directly, expected of y is expected of y given x. We are using 1, it's from 1 again here. And then you can see whatever I have here, I have another formula. It says expectation of the square of expectation of y given x minus the square of expectation of y given x. You can see this is actually a formula for variance. We are actually getting variance of what? It's actually variance of this random variable. We are actually getting variance of this random variable here. The random variable we are getting variance, we are having the formula for variance is actually expected of y given x. That random variable. We are getting variance of this random variable. That's why we are saying expected of the square of the random variable minus the square of the mean of the random variable. See, that's the formula for variance. So the random variable in question, we are determining the variance, or we are finding the variance is actually expected of y given x. So that is a formula for variance of far of expected of y given x. So we have actually shown that expected of far of y given x is equal to far of y minus far of expected of y given x, giving us the result. If you take t to the left-hand side, it would now give us expected of far of y given x plus far of expected of y given x is equals to far of y, property number 2. This property has a name. It is called the law of total variance. The law of total variance. It is actually like saying far of y can be decomposed into 2 components. It is called the law of total variance. That is, far of y has 2 components. The first component is called the expected value. What is this? Expected value of conditional variance. Is it? You can see expected value of conditional variance, which is a weighted average of the conditional variances. That's what it means. It's actually a weighted average of the conditional variance. It's actually averaging conditional variances. Actually, the weights are provided by the conditional distribution of y given x. Hmm. So it is a weighted average of the conditional variances. The second component is called the variance of the conditional means, hmm, which represents, you're not talking about the conditional means. We are now getting and those conditional means are variability. We are not talking about the variance of the conditional means, which represents the additional variance as a result of the uncertainty in the random variable x. If there is a great deal of variation among the conditional mean, if they are very different, hmm, those conditional means, what you are talking about, their variability. If they are very different, that means the variation will be reflected in variance of y through the second component. This will be high. So when this is high, this will be small because the variance of y is just constant anyway, but it can be decomposed into two components. So when this part is high, it will be small. When this part is small, it will be high. Now, you can actually see when we are actually relating two things here. When you are about the conditional mean and variance of y given x, that's what you are talking about here in these two properties. The conditional mean of y given x, and also talking about var of y given x. Both of them are relating. The first one is the mean of y, the second one is the variance of y. So one is about the means, the second one is about the variances. Now, if you relate the two, you can actually see when you are dealing with just experience of y and var of y, you are actually talking about this marginal of y. Associated with this marginal of y are its mean experience of y. These are the statistical properties. Its mean experience of y, its variance var of y. Those are its statistical properties. And you can now see that this marginal of y, we can actually get by integrating out the joint. Integrate the joint over x. And the joint is the conditional of y given x times the marginal of x. This is the joint. And if you integrate that over x, you get the marginal of y. So you can actually see these two properties is about this marginal of y and this conditional of y given x. It's relating those two. It's relating their statistical properties of this marginal of y and the conditional of y given x. Whereas these as mean expression of y and variance of y, this one has expression of y given x and var of y given x. So you can actually see in these two properties, this has to do with that marginal of y. This has to do with that marginal of y. But as far as the conditional of y are concerned, also expect it has got is actually its mean of y given x, and also its variance of y given x. So it is linking these two properties are actually linked through this. Anyway, uh, so that marks the end of those of conditional distributions and what is and all that goes with it. I beg we stop there today. Next time we shall focus on what we call sampling distributions, very important, and then the law of large numbers. So what is remaining on probability are the sampling distributions and the law of large numbers, and then we start statistical inference. I'll be sending you the notes, the next set of notes, notes 5, and probably maybe note 6. Note 6 is on statistical inference. The last notes on notes 5 is the last bit of probability, which concerns now sampling distributions. Very important when you are dealing with applications in barometric inference for that matter. Thank you and have a good evening.
Thank you, Prof.